Have you ever looked at a giant construction crane or even just your kitchen mixer and thought, how does that actually work? It seems impossibly complex, right? Well, today we're going to pull back the curtain on a really cool secret that tons of machines, big and small, all follow just a handful of simple, powerful rules. So let's start by looking at a few things you might know and find out what they have in common.
Okay, let's kick things off with a little puzzle. You've got a tiny toy car, a huge cargo ship, and a kitchen mixer. I mean, what on earth could those three possibly share? They feel like they're from totally different universes. But believe it or not, the connection is that they all use the exact same basic principles to get things moving. And we're about to see how. So our journey starts with forces we can't even see. I'm talking about the air all around us and the water in our pipes. You might think they don't do much, but they have incredible power to push, pull, and lift. You just have to know the secret to unlocking it. Now, think about this for a second. It almost feels like a magic trick, doesn't it? You blow up a balloon, stick it on a little toy car, let it go, and whoosh, it zips across the floor. How is that invisible puff of air making something real move? What's the secret sauce here?
Well, it all breaks down into a really simple three-step chain reaction. First, we cram a bunch of air inside the balloon, right? That builds up a ton of pressure. Then we open the nozzle. Now, nature hates that kind of imbalance, so all that high-pressure air rushes out backward. And here's the crucial part. That backward blast of air creates an equal and opposite forward push on the car. And what we're looking at right there is a perfect everyday example of one of the most important rules in all of physics, Newton's third law of motion. For every single action, there is an equal and opposite reaction. The balloon pushes the air back. That's the action. And so the air pushes the balloon and the car forward. That's the reaction. See? It's not magic, it's just physics. Now here's the really mind-blowing part. This exact same idea, action and reaction, is what shoves a gigantic multi-ton airplane through the sky. A jet engine? It's basically just a very, very powerful and super sophisticated balloon. It yanks air in, heats it up like crazy, and then blasts it out the back at insane speeds. That creates a massive forward thrust. It's the same simple principle, just scaled way, way up. Okay, so pushing air backward is one way to go. But what about pulling yourself forward? Let's talk about propellers for a second. Why are the blades curved like that? Why don't they just look like a regular fan, just chopping at the air? What is it about that specific shape that can actually pull an entire airplane through the sky?
The secret here is another core concept, and it's called Bernoulli's principle. That curved shape on a propeller blade makes the air have to travel a longer, faster path over one side compared to the other. And here's the rule. Faster moving air has lower pressure, so you get this pressure difference between the front and the back of the blade, and that creates a force that literally pulls the propeller and the plane forward. So we've seen that gases like air can be pretty powerful. But when you look at the real heavy lifters, excavators, car lifts, those massive cranes, they don't use air, they use liquids, like oil. So what gives? Why are liquids the go-to for jobs that need just immense force? The whole difference comes down to one simple word, compressibility. Think of air like a sponge. If you push on it, a lot of your energy just gets wasted squishing the sponge itself. But a liquid, like water or oil, it's pretty much incompressible. When you push on it, it doesn't squeeze down. It transfers that push almost perfectly from one end to the other. And that property is what unleashes the magic of hydraulics, all thanks to something called Pascal's principle. It basically says that if you apply pressure to a liquid in a closed container, that pressure is felt equally everywhere inside. So if you use a small amount of force on a small piston, that same pressure gets applied to a much bigger piston, and boom, you get a huge amount of force coming out the other side. It's a force multiplier. And we rely on this all the time, probably without even thinking about it. The brakes in your car that stop a 2-ton vehicle with just a tap of your foot? Hydraulics. The landing gear on an airplane, the powerful arms of a construction digger, all of them use this principle to turn a small, easy push into an incredibly powerful output. All right, so we've figured out how to generate some serious force. But raw power isn't enough, right? You have to be able to control it. And that brings us to our second act, the simple, elegant, and totally essential magic of gears. So here's another puzzle for you. Think about an electric motor, or the engine in a car. It basically spins at a certain speed. So how can that one motor let a car crawl slowly but powerfully up a steep hill and also let it zoom down the highway at high speed? How do we manage that relationship between speed and power? Well, the answer is gears, and they follow a really simple set of rules. Check this out. If you have a small gear that's spinning fast and you use it to turn a big gear, that big gear will spin much slower, but with way more turning force or torque. That's your hill climbing power. Now flip it around. Have a big gear drive a small one, and you get less turning power, but a whole lot more speed. So what this all boils down to is a classic trade-off. You could exchange speed for power, or you can exchange power for speed. But you can't have the maximum of both at the exact same time from the same motor. A gearbox in a car is really just a machine for letting you choose which side of that trade-off you need at any moment.
And get this, gears are even cooler than that. They do more than just manage speed and torque. When you mesh two gears together, they naturally spin in opposite directions. But what if you need them to spin the same way? Easy, just pop a third idler gear in between them. And with a really clever setup called a rack and pinion, you can turn that spinning motion into perfect straight line motion, which is exactly how the steering in many cars works. Pretty neat, huh?
Okay, we've looked at air pressure, we've looked at hydraulics, we've looked at gears, but the real lesson here, the ultimate takeaway, isn't just about the parts themselves. It's about a way of thinking, a way of seeing the world around you. And it all comes down to this one simple idea. Complex machines are just simple principles working together. Next time you see a complicated machine, remember, you're not looking at one big, incomprehensible thing. You're just looking at a collection of simple, understandable ideas all working together in harmony.
I mean, just think about what we uncovered today. Action and reaction, that explains rockets. Pressure differences, that explains propellers. Force multiplication, that's how a crane works. And mechanical trade-offs, well, that explains pretty much any machine with a motor. These aren't just random facts. They are the fundamental rules of the game.
Just four core ideas that we've talked about are the basic building blocks for thousands upon thousands of technologies that literally shape our world. The moment you understand the principle, you can start to understand the machine, no matter how complicated it looks from the outside.
So the real takeaway is this. The key to understanding isn't about having all the answers. It's about learning to ask the right, simple questions. Why is that blade curved that way? Why are they using a liquid here? Why is that gear so much bigger than that one? Because behind every complex machine, there's a simple, beautiful answer, just waiting for you to find it. So what simple question are you going to ask next?